See that people are coming in right now. I'm gonna let people walk through the door for a little longer. The numbers are really piping up though, so we'll be starting in just a second. Thank you everybody for coming again. For those of you who's the first time, welcome for the first time to the Healthy Building webinar series. We're really glad to have you. We have two folks on the phone to talk to you about humidity, the healthy zone. And we can't thank our sponsor, Hedrick, enough. Hedrick has been so generous to be sponsoring two of these webinar series now. And they're just a great company that as a full service manufacturing representative in Western and Northern Michigan. Actually, they also do work in Northern Indiana for you out-of-state folks. Since 1982, they specialized in indoor air quality and thermal management for HVAC for commercial and light industrial applications. So thank you so much, Hedrick. We're really grateful for your generosity. Could you switch the slide, Pasquale? So I'm glad to be back. I've been gone for 2 Thursdays, and it's, this is one of my favorite things to do these days. So I'm Jillian Gim, the program manager for the U.S. Green Building Council of West Michigan. And we have the privilege of having Pasquale Demitrio, head of sales from the HVAC North America of Carel. And then we have John Rumohr, who is a manager of mechanical engineering for Tower Pinkster. So because of all the interest from you folks on the line, we have put together a viewer's interest of deep dive into humidity and deep dive into bipolar ionization. That was last week. So we got some folks together to speak about it, and I cannot wait to hear what Pasquale has to say. So take it away, Pasquale.
Okay. Thank you very much, Jillian. That was awesome. Appreciate the introduction. And thank you everyone for being on the line today. I hope it's very educational for you guys. There is a lot going on right now in the environment, and I think everybody knows why, as why we're talking about, the indoor environment and human health. It's become a very popular topic with this pandemic that we know. So hopefully over the next 20 minutes or so, we can learn something and can help everybody out here. So let's take a look. So for the last, let's say, year or more, I would open up all my presentations with this slide. And it says, what's the most exciting topic in healthcare today? And so what I would do, I'd take a few answers from around the room, and then I'd think I was real clever, and I would say, hey, humidification. And so as I was reviewing this is really not appropriate anymore. Turns out I'm not that clever, because what happens is everybody says COVID-19, coronavirus. So that has become, I don't know if you say exciting, but the dominant topic, I'd say, in the conversation today. So, but the good news is it fits right in with the same messaging and the same information that we've been sharing for the last couple of years. So let's take a look at what that means, okay? So here's a brief overview, just so I don't talk forever. I made it to 5 bullet points. Humans in the healthy zone, pathogens and how they travel, reduced infectivity, and the indoor environment. We can do a quick review, and then just a brief conclusion on how to move forward here, okay? So let's get started. Humans in the healthy zone. So if you've been in the building industry very long, you're probably familiar with this chart. It's called the Sterling chart, and this is from 1985, and this was done through ASHRAE research. I believe it was 11 different studies that were put together, and they came up with this for the first time and published it in 1985. And what it determined was that there's an optimal zone for relative humidity for humans. So it looks like through all 11 studies that we thrive between this 40% relative humidity and 60% relative humidity. And that was the first time it was published. First time that, it was put on paper. Before that, there may have been some military studies and things like that, but this is where it kind of formalized that in 1985. So as good as that sounds, I don't think we took it very serious back then. It was more of, okay, that's an optimal zone. That's a feel good. Maybe it's a comfort thing. So as we move forward here, we start to see how this became a lot more important as we go. So now this study, this is a recent study. Now this was released April 4th, 2019, and this was from Yale University. And what they actually researched, what's the mechanism of action? Why do people thrive in this 40 to 60 zone, and why do they struggle when the relative humidity is lower than that, let's say 20%? And they looked at the mechanism of action. They looked at how do pathogens respond and how do our bodies respond. So to me, I look at it like it's the other bookend. Like we had the Sterling chart in 1985, and now 2019, we have this Yale study that kind of unraveled what they did. So let's take a look at what the results were, and then I have an example for you of how this works. So the results of this study were that they found at 50% relative humidity, you can see on the left-hand side here, our bodies were able to get rid of the virus. So basically they were exposed to the virus and they did not get sick at 50% relative humidity. Or if they did get sick, it was very mild. So just maybe a slight fever or something, but nothing severe at all. And then at 20% relative humidity, that's where they found the big difference. Where people were getting very sick, the pathogens are allowed to penetrate into the tissue and cause a very severe infection. So, and what this study looked at is, I think you guys are picking it up, but what it is, it's how our body, how our immune system is responding to the air, the indoor air quality, and the level of humidity that it's exposed to. So this is what's going on here. It's our internal defense is breaking down in the dry environment, and it's being very protective in the well humidified environment. So as you know, our upper airways, it's the first exposure to the air, our nose, our throat, our lungs, are all exposed and have this constant interchange with the air. So at 50% relative humidity, we have improved functioning, the ability to clear these tissues and these pathogens, and also to repair tissue. So if there was an infection, if it's still kept at a certain level, our body has the ability to overcome that and repair the tissue. So there's definitely an optimal space there that helps protect our human immune system. So let's take a look. I'm going to play a short video for you here. It's only about a minute. Might take some of you back to science class, but I think it's what'd I do? It happens. Stay with me. All right, so can you see that video playing there?
Yeah, I can.
Okay, very good. So you can see that those hair, that's the cilia on the bottom in the throat, right? In our airways. That cilia that's moving back and forth, and that's a mucosal layer. And you can see there's some Corona-19 up here, COVID-19. Those are the pathogens that are being washed through this process. And this is a normal functioning throat, and that's how we get rid of pathogens like that. Our body passes about 150,000 pathogens a day that it's exposed to when it's functioning properly. So, and you can see this is more normal. They slowed it down so you can understand it. And just a few more seconds here, you'll see, now they actually have a camera inside someone's throat where you can see these cilia and how they're functioning. And I'm going to show you something here real quick. So this is actually live. So hold on one second. So see these black marks right here? These are like pathogens. And as you can see, it looks like they're floating. But really what they're doing is they're on top of the mucosal layer. See how they're moving right across the tissue and the cilia? See all the little dancing hairs there? That's passing it through there. So that's a proper functioning defense system. That's our immunodefense system right there inside of our throats. So it's pretty cool. It's kind of geeky, but
it is really cool.
Yeah, but that is let me go back here. Okay. So I show you that just so you guys understand that's what's going on inside. And when we break down, you can imagine that tissue gets coarse, it gets dry, it gets stiff, and that's when the pathogens have the ability to infect us, and that's when we get sick. And that's one thing we know about this coronavirus. It's very heavy into the lungs, right? It's very heavy into our airways, and this is a huge area where we can protect ourselves by protecting our immune systems. So. And I say, so what happens when we stay in a dry room? Let's say you're in a hospital in the middle of the winter, you know, it's forced heat. There's no humidification added into your recovery room. And so what's the relative humidity? You know, I guarantee it's low, probably below 20, if I had to guess, if they're not humidifying. But you think about what's going on there. The universe is going to seek equilibrium. I'm like a wet sponge, right? My airways are 85% water. So if I sit in a dry environment for that long, what's going to happen? It's going to steal my moisture. It's going to steal my moisture and put it into the air. So anyway, that's how we're exposed over longer periods of time. We become very vulnerable in those situations. Okay, so that's one. That's the immune system. That's how we respond. Now let's look at pathogens and how they travel. Now this is interesting. As you see here, when you have particles in the air, the float time changes significantly in different relative humidities. And this was actually taken from a hospital study, this slide. But as you can see on the left-hand side, 40% relative humidity, the particles are larger in diameter. So what happens here, they're heavier, they're not as buoyant, and they settle out on the floor. And then they're very easy to clean with surface cleansing, and all your cleansing materials work, and your surface wipe downs and all that are very effective. As you go over here in the 20% and lower relative humidity, you can see the diameter size 1 or 0.5 microns, very, very tiny. So what happens is they become very light and very buoyant, and they last almost forever. In this study, it says 21 days, but that was because that was all they studied. They didn't keep studying it after that. But so you can imagine the difference in the way they travel. If they're larger and they can't float, they can settle out. And when they're light and airy, even if you come and wipe them in a certain area, a lot of times they can just recirculate back into the air, go into the airstream, and recontaminate other clean areas or infect people. So I think that is significant. This is from a white paper that was done called Breathe Easy, but it gives a visual of as to what happens here with these pathogens. So you can see in the 40 to 60 range, they basically settle out within 3 feet, 3 to 6 feet. I guess that's a magic number these days, right? Social distancing, 6 feet. But 3 to 6 feet is pretty standard when it's well humidified. But when it's dry, very hard to contain these droplets. They shrink up, they protect themselves. They're smart, they adapt, and they shrink up and they become very buoyant, and they seek for that next host. So you can see on the right-hand side there how it can go into your air system or just even in the airways within the facility. Okay, so here's our friend COVID-19. Very, very apparent these days. On the left-hand side, you guys see how many times have you guys washed your hands in the last 2.5 months? We're sick of it, but yeah, contact transmission is primarily, well, what's thought is the primary way, and it still may be the primary way. But in the beginning, if you remember, there was some talk about whether we should wear masks or not wear masks and all that stuff. But I believe anybody who's in the indoor air environment, indoor air quality, understands that a mask can probably help you. And not that we need to wear them all the time, that's not what I'm saying. But certainly you have to believe that there's a potential for airborne infections. So, and that's what we've learned, right? We've learned that now. Now we all wear masks. Every place we go, and we may have to for next year. I'm not sure. That might be a little crazy, but there is some validation to it. So this is from last month. This is from Environment International, and this is the first one that actually studied the coronavirus itself, and they spoke about airborne transmission of COVID-2, the world should face the reality. Basically saying the same things that we've seen in the other studies. You can see the droplets falling to the floor, and the lighter droplets are traveling further and traveling around the room. Once again, it just fits right into what we spoke about previously, but it's nice to see that it's current last month specific to coronavirus. I think it's very topical, and it makes sense. You would assume from what we know of the other studies going on. So it's just almost a verification of what we thought, okay? So infectivity of the virus. So I always thought this is one of the neatest things that I came across when I look at all these studies. And this is a flu study that was done in 2013. It's actually done at the University of Chicago. And what they looked at is the infectivity of that virus at different humidification levels. So as you look at here, I don't know if this is confusing, but I'll do my best. If you look at the bottom is your relative humidity, and then the infectivity rate of the actual virus, okay? That's what it's tracking here. So as you see, if you go from 20% relative humidity and you go straight up there, it's about 80% infective. But as you can see, when you get closer and closer to that 40 to 60% range, right when you get to 40, it's like that magic zone there where the infectivity of the flu virus just drops off. And I mean, it looks like it bottoms out maybe 43% relative humidity. It seems to be like the low point on this one. But you can see between 40 and 60 there versus 10 to 20 to even 30, which is where most of our buildings are in the winter. You can see the infectivity of the virus itself actually changes, which I think this is one of the neatest things, because it just shows that there's, it just shows that there's other things going on inside this environment. And I think it validates the original, the Sterling chart, right? Once again, this falls right into line with the Sterling. I don't think the Sterling chart knew what they stumbled upon when they printed that in 1985, because now you have all these other studies that are coming up with reasons why that optimal zone is that optimal zone. So anyway, I think this is a really neat study.
Cool.
Yeah. And then, so, people ask me all the time, why does this happen? The truth is, I'm not a research scientist, so I can't tell you, but the thought is in the industry is that there's some molecular change going on within the virus, right? So, or within that particle, different elements of H2O are involved. And as we go from 100 microns down to 0.5 microns, there's a change going on within the molecular structure of the pathogen. So that's the thought. I guess research is still to be done on that, but that's the thought. But I think it's pretty neat that all these line up between that 40 and 60 zone. Okay, so indoor environment. This, I just wanted to address. This is where, number one, I guess we spend most of our time, but number two, I see that we can have a huge impact on, you talk about healthy buildings, clean buildings. I think that if we consider this healthy zone and the benefits that it has, and you talk about, like right here, I look at hospitals. We know about hospitals. There's sick people there. There's vulnerable people in hospitals, and we do humidify, but we don't do it very well. We humidify. What am I thinking? Surgical suites, right? Maybe supply areas. We might got to protect the supplies, or else they go out of validation. But besides that, I mean, we don't. There's, I don't think we humidify all the recovery rooms. What about nursing stations, right? Think about the spread of all these viruses, this COVID-19. What's the relative humidity in a lot of these hospitals where all these employees are working? So I think hospitals is definitely a hot spot, and we do humidify some of the hospitals, but I think you're going to see more and more. I think there's they're going to start understanding the benefits of why to do this. The other places I see as what we should be considering heavily is the long-term care nursing homes, right? Think about the elderly population, very vulnerable population. And they're not just there for a visit for a couple of days, they live there, right? 24/7. So they're, you can imagine dry environments make you immunocompromised, you're older, you have comorbid conditions. So that's where I think is a big place where we can help. Schools, obviously, I think schools and universities seem to have a little bit more of a budget. It's our grade schools and our high schools are probably a place where we have not been able to take advantage of this. I'd say budgetary reasons are probably a big part of it, but we can certainly help out there. Our home, you're starting to see more and more homes become humidified, and I think that's a great thing because we do spend a lot of the time. Just think about sleeping. Think about sleeping in a healthy environment versus sleeping in a dry environment where you make yourself vulnerable. And then work in offices. The only problem with work in offices, everybody wants to see what's my ROI, right? Because they're businesses. So that's always a challenge, but certainly there are studies out there that the US government actually has done recently looking at sleep patterns and working in dry environments throughout the day and productivity levels. So I think there's a lot on the horizon. I think there's a lot of things that we've learned over the last, I say 35 years, but really over the last 5 years, 6 years, it's really come to light as to what this means to us. And COVID has brought it all right to the top. It's made building folks, anybody involved in taking care of indoor air quality and providing air systems for buildings, they're going to become the experts in this thing, whether they like it or not. So anyway, so I think I'm running a little late here. I'm not going to play this video, but the idea is that we are part of our environment. It's invisible, but right now, everybody where you're sitting, you're leaving your microbial footprint right where you are. You're shedding as I talk here, right? There's particles coming out of my mouth. I'm becoming part of my environment, and so are you. And that's just, it's part of who we are in every day. So you really can't avoid it. So we have to do our best to take care of it, was what I'd say.
Oh, man, that seems like it would be a cool video to see.
Oh, you want to see it? I'm sorry.
Just a little bit.
Yeah. I just didn't want to run over here too long.
We'll make it up.
So this is actually done by the University of Oregon, Dr. Jessica Green, and this is a video based off of their study. So it just looks at the shedding process that goes on, and you just see as this engineer / architect, you can see that as she's working here, she's shedding of skin particles. You can see, air particles exchanging with the air, but there is this constant interchange that we have with our environment, and the indoor environment is even more particular because outside it's very biodiverse. Inside, it's a limited makeup of what we're dealing with. So the point of this is we have a very high impact on our environment, and our environment has a very big impact on us. So.
It's really interesting to see it that way because otherwise it'll be invisible to us.
Yeah, that's right. It is invisible. And that's why a lot of times, that's why I think it takes so long for us to kind of realize what we're starting to realize today is that it's invisible. It's not tangible. You can't touch it, right? So anyway, that my conclusion is get in the zone. I know it's cliche, but I'm sorry. That's how I am. But, you think about your immune system, how to protect it. Think about the pathogens and how they travel, and think about the infectivity of the virus, right? If you can optimize those three things by providing a proper indoor air environment, 40 to 60 relative humidity, it really can really change the buildings that you're in. So, and that's it. I'm going to hand it off to John here and let you go, and I'll be around for questions at the end if you have. Thank you, John. You're in control. You want to steal the screen?
Great. Thanks, Pasquale. As Pasquale said, and he just gave us all the great reasons why we want to humidify our buildings, all the benefits for health, especially, these are things that we've been doing for decades in some of the extended care facilities and healthcare facilities, but may not have been as prevalent in our schools, in our homes, or in our offices. And again, and mainly I think that's because of both the first cost as well as the long-term operational costs and maintenance issues associated with adding humidification to our buildings. We do hope that changes with kind of that heightened awareness right now with indoor air quality and the benefits to it. I do think there's some challenges in determining what that ROI for adding humidification in schools or in our offices are, and really that's something that needs to be more than just the bricks and mortar cost or the material costs of that infrastructure. I think it really needs to start looking at what is that savings from reduced absenteeism or less sick time for our employees, to really start to be able to look at the holistic picture of what that humidification does to us, as well as just feeling better overall being in our spaces. So as Pasquale mentioned early on, humidification always seeks to look to an equilibrium. So if we're in a very dry environment, moisture is always going to go from the most moist environment to the driest environment. And being that we live in Michigan and have 4 seasons almost daily, looking at our building construction gets to be somewhat of a challenge, because half of the year we're wanting to push moisture outside to the outside of the building, and the other half of the year the outside is wanting to push moisture into our buildings. So we're getting into the summer now. So as my graphic on the left-hand side shows, as it gets warmer out, our moisture drive is naturally going to be taking warm, moist air from outside of the building and wanting to drive it through our wall structures to get to our indoor condition. And then in the winter, much more drastic, because we've got a greater differential, but we're wanting to take moisture that's inside the building and drive it out. And so much of our job as architects and engineers is doing our best to make sure we're not getting any moisture into our buildings. We want to make our buildings watertight. We don't want leaks. And now we're recommending here, let's dump a bunch of water in the air. And how are we going to control that? So, of course, that's a controlled leak, but that means we really want to look at where is our vapor barrier within our wall construction and how does that look? General practices always keep it on the warm side. So you want to look at where is that for the majority of the year. And in our climate in particular, that's generally on the inside face of the wall. But again, I think this needs to be looked at for every building type and climate type, and what your space is really looking at doing. So as part of that, we really think and recommend that if you're looking at adding any sort of humidification to your building, that you are going ahead and having a design professional really do a dew point analysis on what your wall construction is going to be doing for you. In the older constructions, they might not have had as many humidity issues affecting their walls and generating mold and mildew within the walls, because the humidity could pass so easily through it with such low levels of insulation. As we're tightening up our buildings and adding more humidity, we're starting to drive that dew point to be within the wall structure. So as engineers and architects, we need to be looking at a calculation, and this graphic shows that this particular wall structure, when we're looking at what our dew point is, say with 35% relative humidity indoors at 70 degrees, this gradient through the wall is showing that we're going to start going below the dew point within this batt insulation. So now you're losing your insulation capacity for your batt insulation because you're condensing within that wall, as well as now potentially generating a spot to create mold and mildew. With current codes in newer buildings with requiring insulation on the outside face of our sheething, we're driving that dew point further out, and the goal would be to get the dew point to be either not happening within the wall, or if anywhere, it's happening within the exterior portion of the insulation of the wall. So that way we've got that controlled with air gaps in the exterior face of the wall, as well as weeps within our exterior facade that can help get that moisture away from the building, as well as let it dry out over time. So that way we're not trapping it. So often that had gotten trapped on the interior faces of our buildings and just generated long-term issues and really canceled out all of the health benefits for us, because now we're generating mold and mildew, as opposed to trying to get rid of those pathogens within our airspace. So as of course, another factor in that is looking at all of our window constructions as well. Very frequently, you know, we'll see on a cold winter day condensation on the inside faces of our windows. And again, that's mainly because our windows are the weakest point in our exterior envelope, whether or not that's because we have infiltration and air leakage around them, or just because of, you know, poor insulating factor in our windows themselves. So as we look overall in old buildings and looking at adding humidification to older buildings, we want to be making sure that we're either keeping the perimeter warmer than our dew point temperatures, either with perimeter heat. You know, many old buildings have perimeter fin tube along those exterior faces, and keeping those operational based on more of an outside air temperature versus a indoor space temperature will help guarantee that that indoor surface of the wall is above the dew point at all times. But then also looking at as I mentioned, keeping the perimeter warm with perimeter fin tube heat. But if you don't have that option, being able to put slot diffusers along the walls too, so that again, you're continually washing that exterior with heat. These are examples of a couple of projects where we've done recently that are highly humidified environments. The graphic on the right-hand side is a performing arts facility. So as you know, performing arts, wanting to keep our vocal cords hydrated and instruments and pianos hydrated and in tune. This facility, as in northern Michigan, so an extremely cold climate, wanting to keep that space at 50% relative humidity all year round, including when it's -5 and -10 degrees outside. So as an example here, you know, we've got perimeter heat underneath all of the windows. The floor in front of the tall glazing is all radiant floor. And then we've also got slot diffusers along the top above those windows washing that glazing. The last piece with that is having active control of your dew point within the space, or your relative humidity within the space, and keeping it, making sure that relative humidity is staying below that dew point or above that dew point. And by doing that, you can have sensors right on your glazing or on your frames, just to make sure that you're actively controlling that, so that you're not getting to a humidity level within your space that can generate condensation for you or generate future issues. So Jillian, that was my brief piece to add to it, but I'll turn it back over to you and start in on some of our questions.
That was very good. When you brought up the performing arts space in the chat box, someone said, FYI, John can sing.
Right, I know we talked about that last time as well, so.
So I think they'll forever be a part of you here on this series.
It will, yes.
I found this so interesting, both of your contents. Let me share my screen real quick. I felt like I was talking to someone with like deep medical knowledge, and then flip it to deep building knowledge, and how they come together is crazy and super cool. We had an interesting question regarding the flu season from Dave. So it says, lately, I've been thinking a lot about why flu season is in the winter when we still spend 90% of our time indoors in the summer. Would you agree it's the humidity indoors then, not necessarily the outdoor temperature, keeping us indoors more?
I guess that's for me. So my comment would be, yeah, we spend a lot of time indoors. Like, our lifestyle has changed, right? I mean, as a population, we spend an awful lot of time indoors. That's so yeah, in the summer we spend time indoors. Naturally, in the summer, our homes, our buildings, the relative humidity is naturally going to be raised because of the outdoor conditions. So you're going to be in a safer environment just by higher relative humidity. In the winter, obviously, it makes us the most vulnerable because of the low relative humidity. And then another thing is I think when you go from inside to outside too, the outside environment is very, very biodiverse. There's a lot more bacteria. There's a lot more, if you go stand in the middle of the woods, the chances of you getting coronavirus is very, very low, right? Just because it could even be there, but it's just that it's not very effective because there's so many other bacteria that are around. But when you bring that same air indoor, dry it out, and you're filtering, and it's not a natural environment going on, that's when these pathogens really thrive. So yeah, I mean, I'll also consider the fact that the flu is around in the summer too. It just doesn't travel well. It doesn't infect very well, right? It's still here. It just, the environment that it's in is not conducive to it being very effective. So I don't know if I answered it, but I tried.
I think that was good. John, do you have anything to add?
I just agree with that, or I agree with Pasquale in saying that, during the summer, he's absolutely right. The natural relative humidity or the humidity levels are higher, which, as mentioned in the Stirling chart and other studies, that higher natural humidity level just makes the virus less viable, and therefore we have less cases of it during the summer. That risk really increases as we get
there's an.
Yeah.
Yeah, so John may be more familiar with, how the outdoor environment influences the indoor environment, right? I mean, I don't know how, I know it drives it up, but there's seepages and there's leakages right between the two different, and so I think that definitely would influence, throughout the year.
That actually comes to another question that was, so, okay, sorry, to back up real quick. So the participants are on the line. As many of you know, you have the opportunity to send questions in ahead of time. So there's going to be a hybrid between the questions that you were sending in real time and the questions that were given previously. So I'm referencing a question that was given previously about a day or two ago that is well put with this question right here. So with weather, as you're talking about, the humidity is variable. And so with all the things that are going on with considerations of the cold and flu season, and the humidity makes us more susceptible to contracting something, how impactful do you think the role of humidity plays to disease prevention compared with all the other measures that a building can take?
Well, I can answer that because I've been asked a lot about other technologies that influence reduction. I think there's air scrubbers, UV protection. UV is a big one, right? And I would say, these other forms of prevention, they all work to some degree. My comment would be they all work better if your air is properly humidified, right? Because just think about it. Because there's less pathogens in the air that can travel. And even if a pathogen makes it through a UV treatment in a room, but everybody in there is protected, right? Their immune systems are maximized. You're not going to see the result of that infection. So for my comment, I would never talk about other technologies, or, some people want to get into debates. That's not what it's about. For me, I think it's almost like the baseline that you have to establish, and then you do what you need to do from there. I don't know. Once again, I don't know if I answered that, but that's my comment.
And I would add with that, going back to my initial presentation a couple weeks ago, noting the different technologies out there that everybody's looking at right now, they're really meant to work in concert with each other. So just as Pasquale mentioned,
good point.
Having a better humidified environment or the proper level of indoor humidity just makes our own personal health that much better all the time, and then allows those other tools and technologies to work that much better. It comes down to a little bit of a risk assessment on each owner's part on how many steps they want to take with their own facilities.
Right.
Yeah, good point, John. I like that, in concert.
Going back to singing.
The Performing Arts Center that you showed. Perfect.
So we have a question here from Mark. So does your contention that indoor humidity is the foundation for proper IAQ?
Yeah, I would say that. I would say exactly. Yeah. I mean, I think the challenges are what John mentioned, right? Like, can the buildings handle it? What are the vapor barriers? You have old buildings that are drafty. What are the challenges? I think that, but yeah, absolutely. I think that's the foundation. If you can maintain that, absolutely. I think that's the basis of improving a lot of the other functions of the building. And, another thing is, I say 40 to 60. I would say, if you're normally at 20, can you at least get to 30? That's what I would say. Like, can you take steps towards that 40? Maybe it's not, maybe it's too cold and maybe you're getting condensation on your windows or whatever. But the closer you get to that 40, the better our immune system responds. The bugs may still be able to travel a little bit more at 30, but at least we're protected more. So like the closer you can get to that 40 to 60 is what I'd say. It's not always achievable, right? As John mentioned, there's challenges that come along with it. There's budgets that also come into play. So, but yeah, that's what I would say. Like, yeah, I think it is the foundation. I really do.
That's interesting. You put the phrase "Don't let perfection be the enemy of the good."
Yeah, that's right. That's exactly right.
You can't get to 50. 40 and 30 is better than nothing.
Yeah, don't let it be at 15 all winter, right? In a hospital or a long-term care facility, absolutely.
For sure. This is from Jordan. It's a question for John, and so hang with me here because Jordan has a lot. So, John, how do you like to adjust the humidity set points for the building to reduce the risk of condensation as the outside temperature drops? Often it's not feasible in my experience to maintain 40% in the building with our winters. Which one would you prefer? Humidity resets or override set points based on perimeter zone temp?
I would do a humidity reset. If you can look at it two ways. You can either actively put sensors on your perimeter windows and reset your humidity down to make sure that that's staying away from the dew point, or you can do it on outside air, but that gets a little, it's not as strong of a control sequence as a direct measurement of that space, of the temperature, surface temperatures of the wall or window. But I agree, especially in our older building construction, as you get colder, that does get a lot harder to maintain a higher level of humidity in the space without generating condensation.
Sounds pretty good. So Jordan, if you'd like to respond to John, please type again. So I'm seeing, Deb had asked a question in the chat box. Somebody has asked a question previously. So to summarize, I guess, what both of them are saying, what are some first steps to get to 40%? What is just, low-hanging fruit escalated to, perfection, right? So this anonymous person literally has said, what types of products are recommended to keep relative humidity between 40 and 60 range? Do any work better than others? So it bridges well with what Deb had asked in the chat box too.
I think I'm going to leave John for that one.
So I think that starts to get into a little bit of the different humidification technologies that are out there, and looking at, are you doing point of use humidification in individual rooms that are critical to be maintaining humidity, or are you looking at humidifying your entire facility? And so that gets into some different forms of humidification, whether or not and then also whether or not you're using steam or electricity to generate that, steam, gas-fired, or electricity to generate your humidity. All that can play in as kind of a good, better, best scenario in terms of the level of humidification you're going to get, and then what is your long-term maintenance costs and energy costs associated with humidifying those spaces.
Yeah.
So,
yeah, that's good. Another topic, I think one of the questions came in, Jillian, it was about ROI, return on investment.
I'm just going to ask that next.
Yeah, and the cost, and I think that plays into what John's saying here too, is that you know, when I talk to a lot of people and they want to improve their environment, but they don't know how, or they're afraid, or don't have the budget, I always say, the first thing I say is like, just start monitoring it, right? Just start, see where you're at, see what's, see what's going on, talk to John, find something that can help you monitor it, because that's minimal investment, but it gets you off the curb, gets you going. So that's what I would think. But the other thing, when we talk about technologies, being in the humidification space, the technologies have came a long way, and it still takes energy to create humidification, obviously, but I can tell you that it's becoming more and more efficient all the time. The biggest trend in humidification right now is going to what's called adiabatic humidification. So, and what that does, that is where you are basically spraying water into the air, and you're using the energy in the air to evaporate the water molecule and turn it into a gas. Okay, so I don't want to say free cooling, but it gives you it cools the air down, and you're not using electric or gas. You're not using another heat form to make that happen. That's the biggest trend in the market right now. That's what we see, and those technologies are becoming better and better. So when the larger the project gets, and that's exactly, it's a great question. It's like, what's the ROI? I just told you I can, save people's lives, not pass on infections. So there's all these great things. Everyone's like, well, what's it cost? So, and that's okay. That's fair, because it's so you have to talk about ROI. The place we can talk about ROI is in the adiabatic side of this business. You can talk about energy reduction. And because there's other savings, you can get cooling, and you can reduce your chiller times depending on the size of the project. The bigger the project, the easier it is to show that savings. It's probably, 250 pounds an hour and above, you start considering those adiabatic options. But there are ways now, you'd have to contact John here. We could dig in. It gets a little more technical, but there are ways that you can start to look at ROI in the energy side of things that maybe help pay for your healthier environment.
And kind of as a parallel to that performing arts center I discussed, that's about 1,200 pounds an hour of humidification, which I know probably doesn't mean much to a lot of the viewers, but we did an ROI on that against the adiabatic humidification, gas-fired humidification, or electronic humidification. And of course, adiabatic was dramatically more cost-effective, because really all that system consists of is a small reverse osmosis system, so that we're injecting pure water into the airstream, and then a high pressure pump and nozzles, so that we're using that high pressure pump to atomize the air to generate that humidity, as opposed to using natural gas to boil water or using electricity to boil water. You still have an electric cost there, but the cost of running a pump is significantly less than running, electricity to boil water or gas to boil water.
That's a very good point. And you're only talking about from the manufacturer perspective. And if somebody wants to make the ROI or the financial case on absenteeism, presenteeism, like sick days, things like that, that case could also be made too. But what you just said is like a direct, apples to apples, like obvious right here, technology perspective on ROI savings as well.
I mean, very easily, electric is going to be your highest cost system to operate. But it's going to be dramatically less cost to install if you're doing small room by room type applications. Gas fired will be right in the middle and probably gets into your mid-size humidification, and then adiabatic would be recommended for more of your larger systems.
Right.
For sure.
And also maintenance on the adiabatic systems are relatively simple, because you don't have any scale, because it's already taken out up front in the RO water. So it just makes it easy. You talk about, total cost of, you know, for the life of the product or the life of the system, it typically works out very well.
For sure. So I feel like we could go on this topic for a bit, which is really interesting. I'm also gonna want to, excuse me about that, get these other questions answered. So Trevor asks, are there any good resources to make sure you don't hit a dew point? That image was helpful, but would like more like it. Is this something that can be easily programmed into BMS or JACE?
Yep. Trevor's asking if that can be programmed automatically as either an alarm or a control point within the building's automation system. And the answer would be yes, if your architect or engineer has done that dew point analysis for you and can tell you what that wall construction is doing or would be predicted to do during you know, the course of a normal year. So that'd be something that could be programmed as a set point or an alarm point within a building management system. I would maybe even take that a step further and plug for envelope commissioning on new construction that would, again, validate that dew point analysis that the engineer or architect had done during the design phase.
That's really great answer to that. As always, Trevor, if you want to say something more of that, respond in the chat and I'll make sure to vocalize it. So Charles asks, that typical big box store building envelope that exists in HVAC systems make it difficult to achieve 4060 RH. How do you see addressing this challenge? The typical big box store building envelope and the existing HVAC systems make it difficult to achieve 40 to 60 RH.
Yep. So the way that we've seen big box stores is pushing more towards that adiabatic solution, where instead of that adiabatic being installed in the ductwork, that's actually now piping run along the ceiling and actually just discharging humidity within the space with nozzles. So you're atomizing the air directly within the big box space. So that's pretty common in atriums, big box areas, stadiums, you know, large volume spaces where it's harder to do a lot of discharge with the HVAC system. Because the adiabatic, you're probably running a 1/2 inch line size pipe. So it's pretty easy to snake that around where it needs to get to.
So are you saying that to achieve this challenge could be some of the, you know, technology compromises that we talked about earlier about not necessarily using it through HVAC equipment?
Correct.
Right.
Yeah, and I think that's what we're seeing. We're seeing the industry is adapting to be able to handle some of these things. You know, direct room in space humidification is what John's talking about, and that's becoming more common, especially for the big box. You know, high ceilings, high volume spaces. Once again, very efficient because you're spraying water and taking advantage of the energy that's already there. So.
Right. Then tangentially to that point, actually, so meat processing facilities, they're seeing large outbreaks of COVID-19. So how does this relate to humidity, or rather, is this due to humidity? And if so, can this be corrected? Probably without other trade-offs, I assume. That's difficult.
Yeah, I don't know if it's in the meat. It depends. I mean, there's a lot of contact points there, so it could be contact transmission going on in that facility. That's my initial thought, but then you'd have to look at what's the facility, what is the humidification, where is it located, and you know, that's what. But if it's in the product itself, it's probably contact transmission would be my estimation.
Right. I mean, you can't rule it out, but probably not.
Yeah, no, that's exactly right. I'd say, is there an element of aerosolized transmission? I'd say probably, but in that situation, sounds like it's probably contact surface oriented. For sure.
So, oh man, should I go to these questions or to? Okay, sorry, Dave, I'm gonna hit you. So we had to do a mold remediation. Lorador says my house is well sealed, but not too much. my RH still seems to fluctuate directly without RH. Recently, 88-degree day, it went pretty quickly to 40% RH to 55. So from 40 to 55. Would like to keep it at 40 to 50. What might I be missing?
So is this in a house then as opposed to a commercial facility?
It sounded like commercial, but the word house is in here, so I'm thinking house.
So homes do tend to fluctuate quite a bit more than commercial facilities, mainly because a lot of times sizing of the residential equipment doesn't give a lot of dehumidification capacity in your AC systems. So especially if it gets really warm out all of a sudden, now you've lost probably a lot of your dehumidification capacity within your HVAC system, because it's really mainly trying to now keep your temperature correct within the space. So a lot of that ends up being with what your discharge temperature off of your furnace ends up being at that time, your residential cooling coil, and you're probably not getting a cold enough discharge temperature anymore, which is why you're having a hard time maintaining that humidity as it gets, it rapidly swings temperatures outside.
It's a really good point. Then actually, on that note from a question earlier, how does air leakage affect building humidity? How do you change your controls when they vary between a leaky building or a tight building? How do you manage that both?
Yep. So a leaky building is going to require a lot more humidification and a lot more active control for humidification. The number one thing would be getting a handle on your pressurization control of the building first, to make sure, at least from an airflow standpoint, you're not leaking in. You want everything, for the most part, being slightly pressurized. And then you're getting a little bit less influence from the exterior. But just the nature of being a leaky building and not being as tight, you're going to spend more on humidification for that type of a building.
This is the last question, and then we're gonna have to wrap up soon. Oh, maybe two more, but who knows? So with atomizing the water particles, is there a concern or issue with microbial in the water being spread by that process?
So, okay, go ahead.
Okay, we have not seen the FDA give much guidance in use of clean rooms from our interaction as a medical device company. Any thoughts in regards to the situation for either direct injection into the room or into the ductwork which feeds the room? Thanks.
Yep. So the adiabatic uses RO or RODI, so that has been, and it frequently has UV treatment on it as well. So that is a sterilized and pure water system as it's pumping it out to either to the air handlers or to the atomizers out in the space. And frequently that's recirced as well. So that way those lines are never stagnant. So they're generally stainless steel. So you're going to have a very low risk of any sort of microbial growth within that system, because it's continually being treated with UV as well as already being RODI.
Yep, and so I can speak on that also. So just like John said there are precautions that have been put in place to prevent or to make sure that it's a secure environment, a clean environment. And we are starting to see more, medical device companies, clean rooms, things like that go to the adiabatic. And that goes right into ASHRAE 170 in 2017. They allowed us to put adiabatic systems in the hospitals now. So with that being said, there's stipulations you have to meet. It has to be RODI water, like John said. It has to be UV treated, and you can't have any stagnation in the line. So it has to be continuous flow. So you never have potential for growth. So there's certain guidelines, but yes, it's very hygienic. And that's the way the systems are made, because we understand the risk, and that's why they weren't approved before 2017, and they are today, because we've been able to enhance those.
That's really interesting. So with 1 minute to go, I'm gonna take it from here. So thank you, Pasquale and John, for speaking. If there's any questions that you still have from the audience, I understand that we weren't able to get to everything, but here's their contact information one more time for you to take a look at, to contact them directly if you wanted to. Mark is the rep that will be taking care of the questions from Pasquale.
Right.
So thank you very much for attending. So just so you know, I know you've been here a lot talking to the participants. So next week is going to be the bringing your building back online. Our state is open again. How do you do that safely so that you feel most confident in what you're bringing forth to the table, to your occupants, to your clients, to your employees? So as you always know, there's going to be a follow-up survey. So let us know how we did. Let us know you had technical issues, what you thought of this presentation, and what more you want to see, right? So thank you to our visionary sponsors, and thank you once again to Hedrick. We really appreciate it. And thank you to our speakers for donating your time today. Thank you so much.
Awesome. Thank you.
Thank you.
So we'll talk soon.
Okay.
Thank you, everybody.
Take care.